As a quick intro, my name is Karthik, and I'm a data and analytics consultant in Salem, Charlotte. And I started working with machine learning about 5 years ago. And when I was talking to family and friends about it, oftentimes they've kind of been puzzled as to like what exactly is machine learning, which, is probably a common misunderstanding. I mean, it's something that maybe is not well understood. So they tend to ask me, like, is it just like hype, or is it like magic, or, what exactly is it? And I also struggled to explain to them. So what I thought I would do about a year ago, I put together a visualization, kind of a video that I thought would be kind of helpful. So what it really is kind of like a visualization of a machine learning. Now, obviously, with machine learning, we use like 100 dimensions and, many dimensions. So we've got to visualize it, we probably should reduce it to two dimensions and make it slightly simpler to visualize, right? So this is kind of a simplified look at how a machine might learn. So I kind of wanted to start with that because I think that kind of helps to set like a foundation and kind of a grounding point to some of the topics that we'll be talking about today. So if you can see the screen, my browser, I'm gonna show this video real quick. Okay, so what we have here is we have 1,000 blue points. It kind of looks like they're all together, but they're actually 1,000 blue points. And there's obviously a trend that we can see, but the machine, how does it learn that trend, right? So what you're going to see as I play this video is you're going to see a red line that comes up, and you're going to see that red line move, and you're going to see what it might look like for this program to learn this trend of data points. So that's the first example. And then we'll just look at another example as well. Same thing, just 100 or 1,000 other data points in a different trend. And then the machine going through, I just want to pause it here. A few things to point out. So we've got what's called an epoch or an epoch, depending on how you pronounce that. And that number increases, and that's essentially the iteration. So as those iterations continue, you'll see the number of the epoch increase. And then you'll see here loss, which is just another way of saying error or how bad this model is. So ideally, the goal for machine learning is to reduce error. We want our models to reduce error and get better and better as the machine learns. So you'll see that decrease, and you can see this going down as this model is getting better and better. And while this is playing, I'm going to bring another Word document here real quick. This is a picture of the neural network that I used to train these models. And I used TensorFlow. I built a neural network. So we'll talk about all these kind of things. I'm just kind of throwing around terminology, and then we'll kind of dive a bit deeper into what those terms mean. So this is kind of a simpler trend. And it kind of learns that a lot quicker. You can see that, it only took 79 epochs for that. That learned it really fast. And now in this case, really it's just linear, right? It's a linear trend, and it learned that really fast. And so yes, I did actually use this same neural network for all of these in order to learn all of these different data points. And you can think of these as like observations or measurements that we might take in any given situation, right? We plot it out, we have training data, and then we want the model to kind of learn what kind of trend that is so we can generalize it further. So you might be thinking, well, why didn't I just use linear regression for this, right? I could have very well used linear regression. Instead, I used this, huge, confusing, convoluted-looking neural network to learn this. And what we tend to call that is overfitting, because we're using a complex model to learn something that's actually pretty straightforward and simple. So that's called overfitting. And then on the other end of the spectrum, you could look at something that's kind of more like underfitting, which would be something like this. If I had stopped the learning at this point, and this was my model, then we call that a very underfit model, or something that's too simple, right? It's just a line, when really you're trying to learn some type of a curvy relationship with the data. So another term for overfitting is variance, and another term for underfitting is bias, right? So these are types of error. When we talk about loss, we talk about error, and these are types of error that we oftentimes deal with in machine learning. And so it's kind of like competing factors that go against each other, and that's why we essentially have what's called a bias-variance trade-off. What you're trying to do is you're trying to reduce the error, the total error of bias and variance. And so I heard about this a lot when I was learning about machine learning, and I heard about bias-variance trade-off, and I was like, that's great, kind of makes sense because overfitting and underfitting makes sense. But what really didn't make sense to me is why they call one bias and why they call one variance. I mean, as you know, bias is used in many different situations in different ways. Variance is as well used in different ways, like with standard deviation and the spread of data. So I was totally confused. Like, that's great. This is such a central topic in machine learning, but I don't really understand why one has to do with overfitting and one has to do with underfitting. So I went on a journey to try to learn more about that. And when I went on that journey, I actually came across a better understanding of other terms that we oftentimes throw around in machine learning. They're so fundamental to machine learning, but I think this journey kind of helped me to learn more about that. And they all kind of deal with bias and variance. So we're going to touch on these topics as well. And I feel like learning more about this is going to kind of help us to set that foundation before we really understand why this is called bias and variance. So I will get there at the end, I promise, but we're going to take a little bit of a journey. So when you look up online this bias-variance trade-off, oftentimes you'll see this target, which makes sense, right? I mean, because you can kind of intuitively see that you're trying to hit the bullseye, but like there's a bunch of dots over here that are kind of biased over to some other part. So you're kind of missing consistently somewhere, right? So somewhere else. But then I couldn't understand what that has to do with this, right? And then the same way variance, you're getting close to the target, but there's a bit of quite a bit of spread. And so how does that relate to this overfitting problem, right? Okay, so like I said, on this journey, we're going to talk about all these concepts. So I think maybe a more honest title for this presentation might be something along the lines of this. We are going to be talking about some buzzwords. Hopefully in 40 minutes, I'm going to try to get through all these topics. And hopefully at the end of that, you will have a better understanding of this topic. Okay, so to start this journey, we're going to talk about, and I did mention this, right, linear regression when we were looking at that last graph. And yeah, if you look this up on Wikipedia or YouTube, you're going to see a bunch of math jargon. It's probably confusing and no fun. Honestly, it's probably maybe some PTSD from college statistics classes and stuff. So I want to make this a bit more fun. So I thought, well, heck, instead, I'm just going to show some pictures of my family. You're probably like, what the heck does that have to do with linear regression? It actually doesn't have anything to do with linear regression. These are actually going to be our personas for today, right? So what we have here are Sienna and Skylar, who are elementary school kids. And then my wife, who is a CS and math grad. So she actually worked in software engineering as well as, math-related projects. But she changed professions about 10 years ago. Her name's Jamie. So 10 years, I mean, that's really, look at all the advancements in machine learning that has happened since then, kind of like how much more prevalent it's got, even in the last year with ChatGPT and stuff. So she probably missed a lot of those terms, and it's kind of more of a traditional software engineering background. And then, I'll kind of represent like the perspective of a data scientist. Okay, so we do have to get back to linear regression, right? So I wanted to choose an example, and I went back and looked at, this unsupervised learning group, and I was inspired by Karen. She gave a talk last year about optimization, and she used the GPA as her toy example. So I thought, well, let me borrow that as well. So GPA, as you know, is grade point average. And the reason why I'm using this is also because it's something that we can all relate to. We've all had a grade point average. Maybe some still do. Maybe you're taking classes. I was thinking, well, what if we were to try to build a model related to GPA, right? You might take a look at certain things that might predict GPA. You might take a look at how many hours a week of studying did this person do. You might look at how many hours a week they sleep, how many hours a week they play video games, their height, their hair color, the previous year GPA. And some of these you're thinking, well, obviously has no impact on GPA. Like your height doesn't have any impact on GPA. Hair color sure as heck doesn't have any impact. And you're also probably thinking like, well, hair color is like a categorical variable. We're not going to get too much into that right now, but essentially you can't multiply categories with a number. So data science does have a process where you can turn categorical variables into numeric numbers, essentially. So we're not going to go into that process, but just assume that happened. You can turn like, brunette to 1.5 and blonde to, whatever else, right? So you have an intuition as to how strong these things have as a connection to GPA. So you might think like, what I think was probably the most important one is the previous GPA. If you're talking about a student that last year got a 4.0, there's most likely they're going to get a 4.0 this year and probably next year as well, or somewhere really close. So that has a very strong correlation. And when you train your model with all the training data, essentially you can look at these numbers that kind of show you how important these features are. So in the case of previous year GPA, you've got a high number. And then in the case of things that don't matter, you've got a number that's very close to zero, or heck, it probably should be zero. But for whatever reason, this model decided it's going to be 0.0001 and 0.0004, et cetera, right? And then you've also got things that are important, but maybe not as important. So they've got numbers that are, for example, like, the number of hours you study is probably pretty important as well. So that's got a 0.5. And then this is maybe as important as well. Maybe not as important, but it's important. And then, of course, you've got things that you do, probably the worse your GPA is, right? You play video games for 20 hours a week. It's probably going to have a negative impact on your GPA. So let's say it's kind of inversely proportional, right? Statistics terms, inversely proportional. This is directly proportional. Okay, so Slalom loves to get feedback. So I decided to get feedback from my personas, right? So these people, my kids, okay, I want to see what they think about this wonderful model that I came up with. So my kids say, that's too complex, Daddy, right? Okay, fine, fair enough. My wife says that's overfit, right? So it's kind of a statistic term. It's really overfit. The data scientist says, that's like way too much variance. And I put a question mark there because like, how the heck does this have to do with variance? Like too much variance, like you think of it like statistically with a bunch of spread of data. I can't really understand why that's too much variance. So we'll get back to that. But being the good husband and father that I am, I decided to take their feedback and I said, okay, fine. You think this is too complex? Let me make this a bit simpler. Okay. Or, I'm just going to take a look at the number of hours per week that they study. And I'm going to multiply that by half. And that is going to be my model to predict what a new student's GPA is. So that's easy enough. Let's say on average, like for the most part, most students study between 1 hour to 9 hours per week. So then you just multiply that by half and then you've got your GPA. But then my daughter said that's kind of a problem because you can actually technically have a 0.0 and it only goes up to 4.0 for the most part. So that's kind of a problem. So you kind of think of like potentially having to shift this data over. And that's kind of a bias, right? You have to bias it to the left. So in order to do that, you could add like a negative half. And then you have a new range, which is essentially from 0 to 4. So that's perfect, right? So now you've got the number of hours you study. I just have to ask the student, how many hours do you study? I divide it by 2 and I subtract a half and then I get the GPA. So let me go back to the peanut gallery and see what the fam says. That's too simple, Daddy. Gosh, it's like I feel like I'm the father of Goldilocks. It's either too complex or too simple. I need to find like the just right model, right? My wife says it's underfit, and then the data scientist says that there's too much bias. But these two biases are not necessarily related. But I just need to figure out why would we call this too much bias? Okay. So before we go there, I know this is a data science group and an ML group, so we got to relate this back to a neural network, right? So I'm going to compare this very simply to a simple neural network. So you can actually relate this right back to a neural network by drawing a picture like this. I showed that Word document with a huge neural network. This is a very simple one. And it does the same exact thing. You take the number of hours as an input, as an X, right? The number of hours that they study. You multiply that by a half, and then you subtract a half. So this is the bias. And then you get the GPA, which is the output, or the Y, right? So you got the X, the Y, and then, you multiply, you add or subtract, and then you get the answer. Very simple. And then the kids said, I guess my daughter is evidently learning about y-intercept. So she said, that kind of looks like a y-intercept. Funny enough, if you know the equation y equals mx plus b, this is like that plus b term. And I looked up and I did a lot of looking up and researching and, asking ChatGPT or whatever, what does that b stand for? And I could not get an answer. So I'm just going to make it up. This ain't right, but I'm just going to make it up and say that B stands for bias. In a way, it kind of does, right? Because they are related. There are different ways of looking at the same thing. And so my wife said, it also looks like a coefficient and a slope, right? So these are terms, if you look, think back to your math days, you've got, y equals mx plus b. That m is a coefficient, and it's also the slope of a line. So it's a coefficient to x. And if you graph this out, you got the slope of the line as well. And then, of course, data scientists would call that a weight and a bias. So these are just kind of, the reason why I bring all these up is just because different perspectives, but they're necessarily talking about similar things in a different angle. So I guess, in data science and machine learning, we tend to throw around all these terms that sound kind of confusing and convoluted. But if we kind of relate that back to something that is something more familiar to us, maybe it just kind of makes a bit more sense. And by the way, when we look at that complex, the complex model that I built, you can actually also draw a neural network for that as well. You just have a lot more circles, and then all those kind of feed into the GPA, right? So if you have a very weak connection, like hair color, it's almost got no connection. It has no strength. It's very weak in predicting what the GPA is. Whereas if you have previous GPA, it's kind of like a much thicker line. It has a stronger predictive power as far as what the GPA might be. So just want to kind of relate these two concepts together. Sometimes we think of linear regression as a statistics thing, and then neural networks as a machine learning thing. But in essence, I tend to try to bridge the gap because I feel like that helps people to relate to it better. Okay. So the other thing I wanted to call out here is the complex model and the simple model. They're not that different. I mean, essentially, you could actually write that complex model by putting a bunch of coefficients of 0. So there's this notion of going from complex to simple by giving these weights of 0. And so these are equivalent, right? So you could theoretically ask, if you want to train a model with all of these questions, you could ask every student, you could ask them, how many hours a week do you study, sleep, play video games, what's your height, what's your hair color? And then in the model, if you give all these weights as 0, the model will essentially ignore all of these. And it's only really going to actually look at studying and not previous year GPA, just studying and the bias. So just keep that in mind, because that M that we talked about is going to come in handy later on, when we talk about reducing the complexity of a model by making the coefficients or the weights closer to 0. So this is just my terminology. I kind of think of this as a battle of distances. And this is a diagram that I got from online that I thought really well illustrated. This is not the GPA example. It's just whatever else that they had measured and tried to build a model on. But you can think of these, the same as the blue dots that I had in my video. You can think of these blue dots as the observations that they took, and they kind of, graphed it. Again, it has to be two-dimensional because, that's all we can really put on a computer screen. But right now, so just kind of simplifies it. But this blue model is the overfit model. And what that is trying to do is it's trying to reduce the distance between the model and the training data, or the light blue line and the dark blue circles. Or another way of saying that is trying to reduce the distance between predicted and actual, right? So predicted is your model and the actual is your blue dots. So it's, as you can see, it's trying to get it as close as possible to all this data, which is what we call overfit. And probably a better model, or probably the true function, if you didn't have random noise or maybe observational issues, or maybe your measurement system wasn't precise, then the true model would be something along the lines of this orange line. So this is kind of an issue, because like if you were to predict something at this point of X, you're going to get like a very low value of Y, where you really should get a value right there. And this picture didn't have underfit, but I wanted to throw that in there as well. So I just kind of drew a line, what it might look like with underfit a model. Essentially, you only have one input variable X, so you can only have a straight line because it's a linear regression, a linear line. So then in that case, like what we talked about earlier, as far as, getting those coefficients closer and closer to zero is what this underfit model is trying to do, is it's trying to get those weights as close to zero as possible. And it results in a underfit model. And again, you're going to see obviously a lot of error there as well, because it's not necessarily getting close to the data. So our goal in machine learning is to try to get this orange line and not these blue and green lines. So I want to take a quick tangent, talk about distances. Distances is it's a very important concept in machine learning. And so we tend to have to mathematically analyze how similar and how different entities are. So for example, when we clustered data, as you can see, my daughter thinks call this Mickey Mouse data. I guess that's what it's trying to be. But essentially, what our models are trying to do is trying to find some notion of distance so that we can figure out how similar these are compared to these, and how similar these two are compared to this. And then we can then give a classification of red, green, blue based upon that similarity. So just a quick deviation just to talk about one area where distance is important. But the interesting thing is, you might think of distance, you might have a dot here and a dot here, and then you might think of distance as just the straight line between that. But interestingly enough, in data science, you actually come across many other types of distances. So, and this really well relates to the overfitting and underfitting problem as well. We're going to tie that back together. But I want to talk about the different types of distances for a few minutes. So in an alternate reality, I live in New York City, and I work in this New York City slalom office. And this is actually where the slalom office is. I looked it up in Manhattan, and then just assume that this is my house. So I might try to think about how far, what's the distance between my house and slalom, the office. And if I were a bird, then I could fly directly in a straight line. But unfortunately, I'm not. So I've got to take a taxi cab, let's say. So if I were to take a taxi cab in Manhattan, I can't go in the straight line. I would have to go through this grid of streets, and it would be a different distance, right? So that's two examples of distances, but there are actually many more. But let's just focus on those two for now. So you have let's say a bird distance and a taxi cab distance. Now, the distance that you probably are most familiar, when we just say distance, we generally refer to that straight line distance. And the concept of norms, which you also hear about in data science, is something that's very much tied to distances. It's actually very similar to distance. Norm is just a distance between a point and the origin. So if you have 2 points, you might talk about the distance between them. But if you have 1 point, you can talk about the norm or the magnitude of that, which is essentially the distance between that point and the origin. So let's just assume that I'm standing in some part of Manhattan, and I've got a bird in my hand, and then I tell it to fly a quarter of a mile. And I want to plot out all the different places that it can go to in a quarter of a mile. So obviously, if you let that fly everywhere, you're going to get a circle because radius of 0.5 or 0.25, and then you're going to get a circle as a shape. So when you talk about that bird distance, this is the resulting shape, especially when you think about it as a norm, because you can think of yourself as the origin and then the destinations of where all it can go. But here's the question: what about a taxi cab? If a taxi cab could drive a quarter of a mile in every direction, what shape does that actually trace out? I'll give you a hint. It's not a circle. So obviously, the points that I'm going to give you right now, and you can guess in the chat as well. I can't really see the chat right now, but feel free to throw some answers in the chat if you want to guess it. But obviously, if it were to go straight, right, it can go on this street straight, and let's just say that it can go a quarter of a mile. It can end right there, quarter of a mile west, south, north. Those are the easy answers. But if it can't go straight and it goes in a grid, where are all the different places and what shape will that trace? We'll come back to that. But I think I want to get a bit more mathematical. I'm going to draw some pictures to talk about this further. When we talk about distance, when we just say distance, that straight line distance is actually the Euclidean distance. And with math, we know like this is the hypotenuse. So the way that we calculate that is essentially we would take like the difference in the two x coordinates, and then that would be the a, and then you would take the difference in the two y coordinates, and that would be the b. You square those two and you add them up and you take the square root. So that's like the Pythagorean theorem. So you can call it Pythagorean distance or bird distance, or most commonly Euclidean distance, or actually we just call it distance because that's the one that we take for granted. Now, but what if you can't travel directly, right? So if you have a situation where you have to go in a grid, then the equation changes a bit, right? So you've got now, you're going in this direction, and then you go up, right? So you're not going straight. So this would be like the A and the B. You would still take that difference between the x values, and then you take the difference between the y values, and then you would take the absolute value, because obviously distance can only be positive. But there's another reason why you take the absolute value. Like suppose that this is let's say 4 miles, and this is like 3 miles, and then obviously the hypotenuse is 5, a 3, 4, 5 triangle. If for example, this point was down here, you still want to say 4 plus 3, right? You don't want to say 4 minus 3 and get the wrong answer and get like a Manhattan distance of 1, right? So you don't want to have a negative 3 there. So you take an absolute value. And by the way, they do call this Manhattan distance. I didn't just put that map of Manhattan for nothing, and I didn't throw that taxi cab picture for nothing. They also call it taxi cab distance. So these are actually, I guess data scientists are just not that creative. Maybe the guy who named it lived there or something. I don't know. But I guess they think that the only places where there's grids and people take taxis is Manhattan. So that is why I put that map there. And you might have a question now in your mind. What if the taxi cab could not go all the way here? Let's say there was a detour here. This road was blocked for whatever reason. What if it had to stop short and then go up and then go this way? Well, the good thing is, if you still add up the distance that it went to the x axis and the distance it went in the y axis, you'd still end up with the same answer. And yes, even if the taxi went this way and then went like up and then went all the way back here for whatever strange reason, and then went all the way over here and then all the way like in some crazy little thing. If you take all the positives and then subtract out all the negatives in the x-axis, then you're still going to end up with the same a value, and you're still going to end up with the same b value. So that is something to note there. Okay, so I want to rewrite this formula for just a bit. Instead of absolute value of A and absolute value of B, I'm going to rewrite it. It's going to look a bit weird for now, but essentially if you raise anything to the power of 1, you're not changing it. So and then if you take the 1th root of something, you're also not changing it. So essentially if you rewrite that Manhattan distance like this, then it looks a bit strange, but there's a very good reason why we do that. If you can compare these two, the 2 becomes a 1, and I know that's the Spice Girl song, but we're not going to go there. All these 2's become 1's, and they're very similar, except for the 2's are essentially swapped by changing it to a 1. So, like I said, we don't necessarily talk as much about distance, but we talk about norms, which I said is very similar to distance. It's like a magnitude. So there's a technical term that you'll hear in data science, which is L2 norm and L1 norm. If you hear that, essentially this 2 is because you're squaring these terms, and the 1 is because you're essentially raising it to the power of 1, or you have to take the absolute value essentially, but you raise that absolute value to the power of 1, which you don't write because you don't have to, but it is there. And then the norm, of course, the distance from the origin. So we're going to go back to that question, and I cannot check the chat, so I don't know if anybody did anything or if I put you all to sleep. Let me see here.
You're good. I don't think there's any questions or comments yet.
No questions and no guesses for that shape. Okay, cool. All right, so we were talking about the Euclidean distance. If you talk about like the Euclidean norm of 1 from the origin, and you look at all the points, you trace out a circle. If you talk about the L1 norm, then what happens is, oh gosh, so you have a circle here, and then you have a square for the L1 norm of 1. If you have an L1 norm of 1, essentially from the origin, then all the points that are a L1 norm of 1 from the origin traces out a square, or like a slanted square, I guess a diamond, you could call it. And this took me a bit to like look at. I was like, are we really sure about that? But like, just imagine if the taxi had gone to the east 1 mile, right? So that's obvious there. But if it had to stop short and it went 0.75 miles instead, now it has a quarter of a mile left. Let's see, where's that 0.75? Right there, right? So it has a quarter of a mile left. It can choose to go up or it can choose to go down. And so it hits these dots right here. And then if you go half a mile and you go half a mile up, then it hits these dots, right? So that's why all these blue dots are an L1 norm of 1 from this point. Okay, so L1 norm, L2 norm. In math, what we tend to try to do is not stop there, right? We tend to generalize things. And so why stop at L1 and L2 norm? You can actually generalize this into what's called a Minkowski norm, which allows you to put any value for P. You can raise it to all these different values. And you can see, so this guy right here did a very good job to illustrate this out. You've got the square for the L1 norm, and then you've got the circle for the L2 norm, and then you've got all these other options as well, like L3 norm, although that's not hardly ever used. Actually, an L infinity norm, there is an actual use case for this, very obscure, but there is an actual use case for this. But the ones that are common are the ones between 1 and 2. So they're essentially like a linear combination of an L1 norm and an L2 norm. So so my daughter was looking at this and she's like, oh, that 1.5 is kind of like a mix between a circle and a square. And my son said, is that a squircle? I don't know if that's a technical term, but we'll go with it. And so we're going to talk about why you might use a linear combination of that. But we're talking about overfitting, right? So there's a concept called regularization, which is actually a fancy term, but all it is it's just really trying to prevent overfitting. And what I say, and nobody else, I just made this up, right? So I made it up that it's a cousin. I didn't make up this concept, but I just made it up that it was a cousin. But essentially, I find that these two terms are very similar, meaning L1 norms and L1 regularization. So that's why I call it a cousin, but that's not a technical term either. So when you talk about overfitting, what you're trying to do is you're trying to prevent overfitting. So we have this concept of L1 regularization and L2 regularization. And this equation might seem a bit confusing and intimidating, but essentially it is a calculation of how bad your regression model is, right? So if we look at loss, right? We were talking about loss with that previous video. If I can find that. We had that loss term at the top. That can be calculated in many different ways, but in this case, we're looking at the mean squared error. So this first term right here is when we talk about that battle of distances, this first term is actually you're trying to reduce this number. So you're actually trying to make the difference between the predicted and it says original here, but let's just say the prediction and the actual observations. You're trying to reduce the distance between that. So this term right here tries to overfit the model, whereas this term right here is trying to underfit the model, which because it's trying to reduce, like we were talking about, the coefficients. Remember the m term that I was talking about? That m term is right here, y equals mx plus b. We're trying to reduce the norm of these m terms, and that essentially trying to get it to 0, as close to 0 as possible. when we were comparing back here, when we were comparing the complex model and the simple model, when we've got all these zeros, that's what that second term is trying to do. The regularization term is actually trying to reduce those coefficients to 0. Okay, so I think of it like a tug of war. You've got the overfitting guy here, and you've got the underfitting guy here, and you're actually just trying to find some synergy and find equilibrium, I guess. Okay, so L1 is also known as lasso. You might hear that term. I mean, it's really nothing more than L1, and it tends to let your coefficients get to 0, right? So this one right here tends to let more and more coefficients get to 0. So you end up with a very sparse model with very few weights. L2 finds it hard to fully turn off the features, but it would have those things like we were talking about with like 0.01 or something like that. You'd have very close to 0 coefficients when necessary, but it doesn't necessarily get to there. And when we're talking about that linear combination, we have what's called an elastic net regularization, which is a combination of L1 and L2 regularization. I just threw in Minkowski because that's what the name of the distance is, but it's not called that. I just kind of trying to tie together a bunch of concepts here. And so this term here, this lambda, is a way, it's like a constant that you can kind of play with in your models. It's like hypertuning in order to make that regularization tug either stronger or weaker. So if this was 0, if you set it to 0, then you're not going to have any regularization. So it's going to tend to overfit the model. You're going to have a very crazy overfit model. But if you increase this, then so like if you can see my hands, I'm not sure, but like you have a very overfit model. As you increase that lambda, you're going to get less and less overfit to the point of if you had a very, very high number here, then it's going to be very strong. This tug by this guy is going to be very strong. So it's going to get to the point where it gets underfit. So you have to play with that to kind of find that happy medium. So my son was thinking of this is kind of like feeding this guy spinach. All right, we'll go with that. Got to eat your vegetables. Okay, so I want to tie this back to machine learning and deep learning. So these concepts are not only with linear regression, they are also used in, like, this is just code that I pulled from online, which has a regularizer. And you can see the L2 here. You can use an L1 option as well. And this is your lambda term. So this is just trying to penalize these weights, right? So of course, you might think like, well, if you penalize it, won't it get down to 0 and you're going to get rid of all these things that you might need. So what the gradient descent will try to do is it'll try to push those weights further and further down until it realizes that the overall error is going up. So then it kind of tries to find that happy medium during the training process. Yep, get those weights closer to 0. That is right. Okay, so we talked about a lot of stuff, and I haven't even actually tied this back to bias and variance. So that is actually what I've got to do right now. Let me just kind of see if I don't even know where this. Okay, all right. So how does this actually relate to bias and variance, right? So the thing here is that the kind of missing piece that helped me out was this concept of sampling in machine learning. And in ML models, machine learning models, oftentimes you don't have access to the full universe of data. So to give a quick example, when you talk about this classic machine learning issue of classifying pictures of dogs and cats, you can think of like taking pictures of dogs and cats and training a model, but there is no practical way you can take a picture of every single dog and every single cat. And you can also, even if you could, you can think of like the dog might be running at the time, the dog might be sleeping, the dog might be eating, and it just turns into a combinatorial explosion of the number of combinations of pictures you'd have to take. So you have to like take a sample, and a representative sample is very important. So in this case, suppose there are like 300 million students in the world with GPAs. You can't reasonably collect all this information about all these students and train a model that way. So you take a representative sample. And so let's say we build models with like 10 million random students and 10 million random representative sample students. And you build one model with that, and you ask them, what's your GPA and how many hours a week do you study? And then you take another 10 million and you do the same thing. You take another 10 million, take another 10 million. We say that that's underfit, right? So if you think about this situation where you take a representative sample of 10 million, 10 million, 10 million, and then you build these simple models, but by asking only that one question, well, also the GPA, because you need to be able to train it with the answer, then what you might end up with, if you imagine what these models might end up with, you're going to end up with a y equals mx plus b of, the GPA equals a weight of 0.49 or 0.51, very similar numbers. And then the bias might be very similar as well. And why is that? Well, if you have 10 million students that are representatively sampled, then what you're going to end up with is you're going to end up with a distribution statistically that is very similar. So in machine learning or in data science, we call that like a KL divergence of a very small divergence. So they're going to probably have the same average. Maybe they're all going to have like kind of like an average of, let's say they study 4 hours per week or whatever. And then you're going to have a standard deviation that's very similar as well. So these models really can't distinguish with just that one attribute of how many hours a week they study. So what's going to end up happening is you have this target, right? So where does this target come into picture? If you have a new student that none of these models have seen, that becomes your test case. And you ask that student, how many hours a week do you study? Let's say that student says that they study 7 hours per week. So what your model is going to do, what each of these models will do is they will take that 7 hours and divide it by 2 and they get 3.5, and then they'll subtract a half and they'll get 3. So their answers are all going to be around 3, maybe 3.1 and 2.9. They're all going to be around the same. All of these potential models from a simple models, but they're all trained on different sets of data. And the answer, the true answer, the kid says, instead of 3, the true answer is like 2, for example. Let's say his actual GPA is 2. So that's the target that you're actually trying to aim at. But all these models and all these blue dots are these models, they end up getting an answer of 3 instead. So there is that bias. They're all getting very similar answers. There's not much variation because there's really not much room for variation, but they're all biased towards a certain direction. Now, we don't talk about underfitting much in machine learning because in machine learning, you don't usually start using machine learning models unless you're talking about very complex situations with very complex models. So oftentimes you won't hear someone say like, don't underfit your data. Oftentimes what you'll hear is be aware of overfitting your data because they are complex models and you don't want to get it too complex. So what does variance have to do with this? Well, now you can think of the situation that we talked about with all those things like height and hair color and all the other stuff that we asked them, like the previous GPA. And you build these complex models with 10 million students here and 10 million students here and 10 million students here. And now with those models, there's so many more degrees of freedom for these models, right? So it can play with the M here and it play with the M here and play with the M here and play with the bias here and do all these crazy things. What are the chances that all of these models would end up with very similar weights? It's statistically low. And the reason for that is we do some like random weight initialization. So they might start at different places for each of these. And then just the stochastic nature of gradient descent, they're going to essentially find, and this is getting a bit technical, but they're going to find potentially different local minimas. So they're all probably going to find very similar GPA answers, and they're probably going to be very good at that. But one is going to focus maybe a bit more on height, and the other one might focus a bit more on sleep. It's just because that just happened to be something statistically that happened to be more prevalent or whatever in that specific set of data, right? These 10 million maybe there were a bunch of NBA players, and this one maybe just happened to have, maybe more with like brunette hair color or whatever it might be. So it just kind of started to memorize that kind of feature a bit too much. And then it kind of threw it off slightly. But what you're going to end up now is if you ask a new student all these questions and you have these models spit out their answers, what you're going to see is these models, so these blue dots again are these models now with these very complex training models. And they're all going to have, so let's say that the person's GPA is actually 3.0. they're all, and one might come back and say, oh, I thought it was a 3.1, might say 3.2, 2.9, 2.8, whatever it might be. They're all very close, but they have that variance, right? So the variance is that spread in results. Now, if you average all these out, all these different models, if you average them out, you're going to end up with probably the right answer. The true GPA is hidden there. It's just that they all kind of were slightly off. So the concept of averaging out like kind of slightly not overfit models is kind of what we call like ensemble methods. But that's a topic for a totally different day. We're not going to get into that right now. But just this intuition of maybe don't overfit your models because it's computationally intense. You don't have that compute power, you don't have the time, and it's not practical. You can kind of get it to be less overfit, but you train a bunch of them, and then you make them all kind of get their answer, and you take the average, and that's going to be very close to the true answer, hopefully, if you did your data engineering and data science correctly. So I hope that kind of ties it all together back to why we look at these targets. And I just want to do some shameless plugs, just like Rachel did earlier. So and I can't believe you used that same term, shameless plugs. So my favorite channels for these topics, Ritvik Math, I learn a lot from him. StatQuest, they have totally different styles, but they really talk about these concepts in a very approachable way. And of course, 3 Blue 1 Brown, he's got some really good videos as well, whether it be math or computer science or machine learning. And I also have a series. That video that I showed is kind of like the first one in that series. And then I kind of, this concept of linear regression to neural networks is something that I like to do because I feel like people can relate to linear regression, but maybe not as much to neural networks. And they probably don't realize that the concepts can be very similar. One kind of is like a logical extension of linear regression. Now, obviously, you throw in more concepts, you throw in like activation functions, you make your networks look a lot more complex, but essentially you're still multiplying and adding. You're multiplying weights and you're adding biases, I think is the plural term. So, you can check out those videos as well. And I really appreciate your time.